This video is going to be a different approach yet to all my other videos, and I hope you find it useful. In these times, particularly with a certain virus in the air, literally, I think a lot of people are worried about disinfecting stuff more so than they are at other times. And one sort of machine has caught my eye, which you can now buy on Amazon. It's down as a detergent maker, and it purports to make a dilute solution of bleach or sodium hypochlorite. And there are various guises of these machines. I'm not talking about all of them. I will just discuss the one. It's available for just short of £30. Yes, here we go. So my first nitpick is that it doesn't actually make a detergent. Detergents are things like soaps. They lift off difficult stains by making them partially water soluble. This machine purports to make sodium hypochlorite, or even better, hypochlorous acid, but that depends on the pH. Now, I don't think there's any chance of making hypochlorous acid, as one of the reviewers stated, because the pH is just against it. So the working principle of this is actually simple enough. You have water, you put salt into it, as we know it, or sodium chloride more precisely, and it makes sodium hypochlorite. So how does this work? Well, at the cathode, which is the negatively charged electrode, you react sodium ions and you give them an electron back and it makes sodium metal. The sodium metal would react with the water and make sodium hydroxide and hydrogen gas. Now, I know that a lot of people say, okay, it doesn't form sodium metal first, and that's fine. It's just a way of thinking about what actually ultimately happens to the sodium. And if you had a melt, if you had a non-aqueous melt of sodium chloride, what you would get is sodium metal and chlorine gas. Which brings us to the anode, the positively charged end of the operation, and there you get chlorine gas. So Cl minus, which has an excess electron, not excess electron, but has an extra electron, gets that taken away and it gets oxidized to chlorine gas. So overall, the setup should produce sodium hydroxide, hydrogen gas, and chlorine gas, as you can see my slide. So this is where I had my first thoughts about this. So there's a reason why we don't tend to allow the general public to make chlorine, because chlorine is very toxic. A concentration of 30 to 40 ppm. I was brought up with 550, 500 ppm. Sort of that's it's not accurate, but it's a good sort of, it's a good range of numbers to think about. I still remember that the accurate numbers are actually less good to think about in that sense. So you can detect it at roughly about 1 ppm, but at 5 ppm you might get an irritation of your mucous membranes. At 50 you would certainly suffer from some sort of breathing difficulties, and at 500 ppm, that's parts per million, you would die, basically. So you start off by electrolyzing sodium chloride in water, and that makes chlorine. So the chlorine then bubbles out of the solution because it's a gas and bubbles into the container above the electrodes. So it's going to build up some pressure. Two things can happen. Either the machine is self-contained and the pressure can't escape, or it does escape, so you get chlorine escaping. It doesn't matter how well you've designed it, some of the chlorine will simply not react with whatever is in the water, and we'll come to that in a second. Making sodium hydroxide is also problematic because it's corrosive. It's actually, in a lot of ways, more dangerous than acid. So if I had a 1 molar solution of hydrogen chloride, I would quite happily sit that on my hand, and I've done that in my lessons, and it's fine. It's about the same strength as stomach acid, so it's not a problem. But a 1 molar hydroxide, any hydroxide, sort of sodium hydroxide, well, not any, but sodium hydroxide or potassium hydroxide, that will actually saponify your skin, and it will cause damage to your skin. And so that's problematic. And potentially making sodium hydroxide with chlorine escaping, that's a problem. We'll come to that again later in a bit. You also make hydrogen, and hydrogen is also problematic. It's explosive. And when you've got chlorine gas and hydrogen gas in the same container, and you supply a flash light, maybe, well, I used to do this. I used to fill containers with hydrogen and chlorine gas and then shoot a flash at it, a photographic flash, and it would simply set off the reaction and explode. And that's because the formation of hydrogen chloride is exothermic, and there's actually a minus missing here. It should be minus 92.3 kilojoules per mole. That's just a well, every error is an opportunity to improve. So for comparison purposes, methane has a enthalpy of combustion. So I'm not comparing like with like, but it's got an enthalpy of combustion that's about 9 times higher, let's say. Okay, so there is some energy to be had, though, which is not surprising because you're putting electricity in to split it up. So that's endothermic. And then you are reacting it back again, and that's going to be exothermic. Okay, so theoretically it's possible because bleach, in this case sodium hypochlorite, can be made by bubbling chlorine through a dilute sodium hydroxide solution. Hypochlorous acid is made by bubbling chlorine through water, but you can also use a salty solution of water as long as the pH is below 5.5. And in fact, it needs to be quite a bit below 5.5. So there's a possibility here, but it's a challenge, and it's a further problem, really. The pH will increase with increasing sodium hydroxide production, particularly at the beginning. So you will make sodium hydroxide, and you will bubble through chlorine through a solution which contains almost no sodium hydroxide. And if the reaction simply isn't fast enough, and it won't be because gases are really ineffective at reacting with solutions because they're gases, then it's going to escape. Some of it is going to escape. That will raise the pH of your solution, and you will not get hypochlorous acid. So, and then there's my final thought about what happens to the hydrogen gas. I mean, hydrogen gas is not easily contained, so it might simply escape. But so might the chlorine. So you have, let's get my funky pointer back. You've got sodium hydroxide reacting with a chlorine molecule, and that gives you sodium chloride in solution, of course, and sodium hypochlorite, and it gives you a bit of water. So there's 2 O's there. You can see that, 2 O's, because there's a big 2 in front of that. So there's 2 O's and 2 H's. And you get 1 O here and 1 O there. The 2 H's from here make the water, and one of the chlorines makes the sodium hypochlorite, and the other one makes the salt in solution. Okay, so in detail, what that means is that the chlorides in the solution get taken their 2 electrons that they have away, and it makes chlorine at the anode. And on the previous slide, I had polyana never cries, so that's a very good way of remembering it. Positive anode, negative cathode. So what happens at the cathode? At the cathode, you get, I've been annoying and just gone with the reduction to sodium metal, which of course doesn't happen because the sodium then reacts with water. So there's a further reaction, if you like, at least if you look at it from that sort of detail. You've got 2 electrons coming out, 2 electrons going in. So overall, when you add it all up, you get to the equation of 2 sodium chlorides, giving you 1 sodium chloride and then a sodium hypochlorite and some water. And the reason why the H2 is in brackets there is because it goes away. And of course, the reason why the Cl2 here isn't in brackets, because I'm assuming that it's all going to dissolve in the water and not going to also escape, which is not a really good thing to do. But there we are. Okay, the start of the reaction, we have 1 or 2 grams of sodium chloride in 80 milliliters of water. So that's what what they recommend. So we're going to take 2 grams of sodium chloride. And since 1 mole of sodium chloride is 53.5 grams, 2 grams would therefore be 0.034 moles. I do like to do things in ratios because it makes it just so much easier. So 2 grams in 80 milliliters is about 2.5% by mass. So the conductivity of salt water, link in the description, is obviously increases as the salt content increases. And you can see it's pretty much linear, okay? Whenever I, by the way, calculate anything, I round it up in favor of the product. So I'm going to give it the maximum benefit of the doubt, so to speak, which sometimes is significant, sometimes it's not. Okay. So at 0.5% of sodium chloride in water, the conductivity is 8.2 millisiemens per centimeter. And the per centimeter is important because the distance between the electrodes is significant in determining how much resistance there is to the charge being transferred. In other words, if I have a larger distance, then the charges are going to find it more difficult to go through the water. If the distance is shorter, then charge transfer is going to be increased. The millisiemens is basically an expression of how willing the water is to carry those charges. And you can see it basically doubles with every doubling of the percentage. Okay, so at 2.5%, which I calculated on the previous slide, you get about 40 millisiemens per centimeters. And I've done some rounding up there for the product. Okay. So as I said, 1 Siemens is the reciprocal of resistivity or resistance in water. And I'm going to keep it simple. Basically, 1 Siemens, if you take the reciprocal of it, you get the resistance in ohms. Okay. So how much electricity are we talking? Well, now I have my doubt that it actually delivers 5 volts and up to 2 amps. That to me sounds like the USB charging port that maybe charges up the internally supplied battery. But I'm going to give it the benefit of the doubt and say, okay, as long as it's plugged in, there's maybe a chance that it'll get 5 volts and maybe up to 2 amps. The important thing here is to realize that it's up to 2 amps, because if there isn't anything to conduct the charge in the water, then you can supply the 5 volts all you want, but the amount of current is not going to reach 2 amps. So I've already talked about the distance, the importance of the distance between the electrodes, and I took it as 1 centimeter separation between the electrodes, because that to me sounds reasonable in a device that's about 5 centimeters wide. Now, there are various objections that you can make to that, but we'll see where we get with this calculation, and then I promise you, I'm going to be as generous as I can with the machine at any point, okay? So how much stuff do you start with, and how concentrated could it get? 2 grams is 0.034 moles of sodium chloride. So since we convert 2 moles of sodium chloride into 1 mole of chlorine, that gets us to a maximum of 0.017 mole of chlorine, Cl2. Okay, chlorine gas. The first step is to recognize that the chlorine makes the same number of sodium hypochlorite ions. So for 1 molecule of Cl2, I get 1 molecule of sodium hypochlorite. And the molecular mass is 74.5 grams per mole. So if I have 0.017 mole of my sodium hypochlorite, then that's 1.2665 grams roughly, which when placed in 80 grams of water is about 1.58% weight for weight. So bleach is around 5.25 to 8.25%, and that's because it's not a nice substance. You can't sell it as a very concentrated thing for a number of reasons, but safety is one of them. But as a disinfectant, it's only 0.5 to 2%. So let's call it 1.6% is pretty spot on. So if you could get there, if you could convert that 2 grams of sodium chloride effectively into sodium hypochlorite, then I would agree you have yourself a disinfectant there. So how much electricity does actually flow? In a 2.5% solution with a conductivity of roughly 40 millisiemens, where you've got a voltage of 5 volts, you can use Ohm's law. The resistance is 1 over 40 milliohms, which gets you to about 5 over 25. That's 0.2 amps. Okay. So then you use this equation here, which explains the transfer of charge. The transfer of charge is 0.2 amps times 180 seconds, because each cycle runs for 3 minutes, it says. So that gives you 36 coulomb. The problem here, which I will not address right now, but the problem here is that the resistance will tend to increase as conductivity decreases. So as you take the sodium chloride out of the water, you actually find that less and less charge flows. But let's ignore that for the minute. Then we can use Faraday's law for electrolysis, which is that the mass that you get out of your deposition of material is the charge times the molecular mass divided by Faraday's constant times the charge on the ion. So that's thankfully relatively simple because we have the Coulomb, 36 Coulomb. Then we've got the mass of chlorine, which is molecular mass of chlorine, which is 35.5. Faraday's constant is this monster here, rounded to some extent, and the charge is 1 because chlorine is -1. So that gives you 0.13 grams of Cl, which is of course half of Cl2. So since you don't get Cl on its own, you get Cl2. That's 0.066 grams. But this is at maximum current for 180 seconds and maximum efficiency of absorption of the gas in the solution. So that becomes important for later. So if you have 0.066 grams of chlorine gas, then you make 9.3 times 10 to the -4 moles of sodium hypochlorite. That would be the maximum yield. You could make 0.017 mole of chlorine gas, but according to the calculation, you just make 9.3 times 10 to the 4. That's a lot less. That's 0.00093 moles. If the electrodes are 1 centimeter far apart, so let's say they are only 5 millimeters apart, then the amount would double because the conductivity in the solution would roughly double, and then you get twice as much stuff out. But even then, you are at 1.86 times 10 to the, that should say -3, so it should be 0.00186. Fine. So this is where I have to do a little guesswork. So this is with the power supply essentially supplying 5 volts and 2 amps. Ideally, you would want to see most of the sodium chloride to be electrolyzed in that machine. So you can now say, okay, maybe the electrodes are closer together. Maybe there are multiple electrodes, right? Multiple electrodes would get you around the current restriction. So you could have 5 volts or whatever the battery can actually deliver, and you could have like all of that in parallel. And that's where I had the idea to look at it from the battery point of view. So it's supposed to work from the battery only. How much electricity can the battery supply? We know that the capacity of the battery is 300 milliamp hours. And the working voltage is given as 5 volts, but I've said before that sounds more like the charger. I think I looked up lithium-ion batteries, and they typically have a voltage around 3.6 volts, which would be 1.08 watt-hours or 3.8 kilowatts. And that sounds a lot, but that would be all of the juice in the battery. And each cycle runs for 3 minutes. At 3.6 volts, the current would be, again, given by Ohm's law, with a separation of the electrodes of, let's say, 1 millimeter and a conductivity of correspondingly 10 times as much. Actually, I've rounded it up to 450, just, for shits and giggles. The resistance would be, let's say, 2.2 ohm, which would allow for a current of 1.63 amps to flow. And you could have a number of electrodes all in parallel, right? Even with a bigger separation, you could roll back from that 1 millimeter separation. So that there should be no problem in actually draining the battery. But batteries, if you want to reuse them, you can't overtax them. You can't just drain them at whatever level you want. And the reason why the capacity is given in milliamp hours is because these batteries are good for discharges of 30 milliamps over their lifespan, basically. And that gives you a problem because now we have a small amount of electricity going through. Okay. So assuming that it doesn't matter that we want to treat the battery well, but we're also not killing it in one go. So we're going to say, okay, instead of a tenth of the discharge potential, we're going for all of it over the 3 minutes. And then the charge transferred is 54 Coulomb, and we can plug that basically back into Faraday's law. And then you get 0.02 grams of chlorine. And we can again calculate that is 2.8 times 10 to the minus 4 moles. And that is still less than on the grid. So on the grid, we had 9 point something times 10 to the minus 4, 9.3, I think it was, times 10 to the minus 4. And, okay, so you can say, well, maybe that's enough. Okay. But turns out that if you've got 2.8 times 10 to the minus 4 moles of chlorine gas, then you make the same number of moles of sodium hypochlorite. So you multiply it by 74.5 grams, which is the molar mass of sodium hypochlorite, and you get to 0.021 grams, which in 80 grams of water is around 0.03%. And that, my friends, is basically useless. It's 100 times less concentrated than disinfectant ought to be. I called it homeopathy, which is, probably it's probably better than homeopathy, but there we are. Okay, but here we have more problems. So as the sodium chloride is depleted, even though it won't be depleted by much, the conductivity of the salt water decreases. So the only thing that's going to happen to the process over its time is it's going to become less efficient. But okay, so because of the numbers involved here, they're so small, it's probably not going to impact on the performance. So initially, you also won't have any sodium hydroxide in the solution. So the chlorine gas is going to mostly bubble through that solution. So let's say after 3 minutes, you have, let's say all of the chlorine gas has bubbled through the solution and not reacted with the water. Now, again, that's the worst case scenario, I appreciate. So in the best case scenario, you make hypochlorous acid, but the pH would have to be a lot short of 7, and it is going to be 7 with tap water. In the worst case, you now have chlorine gas in the air. So let's do a quick sort of surmise of that. The question is, how much chlorine actually do you have in the air? And with that amount of chlorine in the air, let's say you leave it running in a kitchen, which is 2 meters by 5 meters by 2 meters. So it's like a galley kitchen, I would say. Then that's about 20 cubic meters. 1 mole of a gas is 22.4 decimeters, so that's 22.4 liters. In 20 cubic meters, you have 20,000 liters. So 2.8 times 10 to the minus 4 moles, according to Avogadro's principle, would fill a volume of 6.2 times 10 to the minus 3 liters. Okay, so that's a vanishingly small amount in even a reasonably small kitchen. And you can calculate the percentage of that, and it's 3.13%. But as a chemist, I'm more interested in ppm, and that's about 0.3 ppm. So what does that mean, 0.3 ppm? And again, just to point out, I may be being completely unfair, but I basically said all the chlorine would escape into the air. The size of the kitchen is fairly small. But essentially at 0.3 ppm, you would smell it. And at 1 to 3 ppm, remember my 550, 500, it's a little bit less than that. Okay, so essentially you could smell it, and maybe that's enough for some people. Maybe because they smell it, particularly in the vicinity of the so-called detergent maker that actually makes sodium hypochlorite and not a detergent, that actually, that smell is going to be most intense. And maybe when you spray it, you will get a little bit of the chlorine smell coming out, but it's not going to be effective as a disinfectant, as a proper disinfectant. As a result, my verdict is that I'm still skeptical. Bubbling gases through a solution is very difficult, and it's very difficult to absorb. Then you have to have sinter stones and stir it maybe, but it doesn't sound likely to me. And another reason I'm skeptical is actually nothing to do with the science. That's almost how I started the video, which is that letting people make chlorine gas or sodium hydroxide solution that you can then spray on stuff and touch and clean up with. As a manufacturer, I would not be happy. The advantage of that, if it worked, which I don't think it does, but if it worked, is you could make it in the bottle and you wouldn't have to touch it, right? So if you wanted to make disinfectant from a bleach that you have at home, you would have to dilute it, and every dilution is problematic. So if you have a 5-point-something% solution and you dilute it 1 in 10, then you get a 0.5% solution. It's not difficult, but it's handling bleach and all that sort of thing. But then I guess you handle bleach by just chucking it down the loo if you wanted to. I think that mostly this is, I don't think it's intended as a scam, because the initial numbers show that if you actually electrolyzed all of the salt, you could get there. But I think it's more intended to reassure people through that, and I'm going to mix my metaphors here, homeopathic smell of chlorine, right? Is that a mixed metaphor? I'm not sure. Mixed science ideas or non-science ideas. But essentially, that's what I think is going on. So I hope you found that useful. Don't be put off if you want to try it. If you want to send me one of these machines, I will actually do so. I will actually do an experiment and try and replicate some of this right here in my conservatory. But I don't know when I'm going to get to it. So I hope I'll see you later in the next video. Bye.